So now we'll start with another definition of the stability, that is bounded input, bounded output stability. So far we have seen the definitions and some of the key results in the sense of Lyapunov or the internal stability, which is mainly concerned with the effect of initial conditions. So we had not seen with respect to the control input U. So this particular concept of stability deals with the when the input is also included in the definition. So we now consider a distinct notion of stability that ignores the initial conditions and is concerned only with the effect of the input on the force response. So far what we had seen about the internal and the Lyapunov stability, we have considered the homogeneous systems. So here we will consider that the initial conditions are 0 and the output or the state is only affected by the input given to the system. So we shall see that for LTI systems that these two notions of stability are closely related, that is the bounded input bounded output stability and also the Lyapunov stability. So we'll start with the continuous time linear time varying systems, where all these matrices A, B, C, D are the time varying matrices. So first we'll start with the continuous time. So we had discussed in the first week that the force response of the system is given by this equation. So here we have specified Y with the subscript F, which denotes the force response, and we also know that the total response of the system Y is one component comes from the homogeneous plus component comes from the force response. So this homogeneous component is because of the initial condition x0 and this force component is because of the external input U. So now we will we'll see the definition of the stability when we have the initial condition equal to 0, meaning to say we won't see this response. Okay, we will only concern with the force response. So the definition of the BIBO stability is given as that the system continuous time linear time varying system is said to be uniformly bounded input bounded output stable if there exists a finite constant G. So here you can consider the factor G as a system gain such that for every input U, its force response Y of F satisfies this inequality. That is to say that the supremum of the norm of the signal Y of F for over T or let's say for all T greater than or equal to 0 is less than or equal to the gain G multiplied by the supremum of the norm of the signal U of T over for all T greater than or equal to 0. So this is the key result for the bounded input bounded output stability for the LTV systems. So these two following statements are equivalent, that the system is uniformly BIBO stable. Second, that every entry of the matrix D of T is uniformly bounded, and the supremum of the integral over T greater than or equal to 0 of this integrand is less than infinity for every entry Gij T comma tau of this matrix. Okay, so again we will see the proof in two parts. So this is the when we say that these two statements are equivalent, we actually want to show that one implies 2 and one is implied by 2. So if so once we have proved both ways implication, meaning to say that one is actually equivalent to 2, and this key result speaks about. So first we will see 2 implies 1, meaning to say that if every entry of D of T is uniformly bounded and this condition is satisfied, then it implies that the system is uniformly bounded input bounded output stable. Now see that the conditions in 1 implies that the gain G is finite. If we go back to the definition of the uniformly BIBO stable, so we say that the system is uniformly BIBO stable whenever there exists some finite gain constant or finite constant G such that this equation is satisfied. Okay, so either saying that the system is BIBO stable or there exists a G is equivalent. So we actually going to prove that there exists some gain G which is finite. Okay, so let's start with the response, the force response of the system, which is given by this equation. If we take its norm, both sides, so we can say that the norm of the signal by f is less than equal to the individual norm of these two signals. And this comes from the property that the multiplication of two matrices, or the norm of the multiplication of two matrices, is less than equal to the multiplication of their individual norms. Okay, so this inequality comes from there, and similarly we apply this property onto the second part. Okay, for all t greater than or equal to 0. Now let's define two signal or two scalars, mu and delta. This mu is given by when we take the supremum over t belonging to 0 to infinity for the norm of the signal u of t, and delta as the supremum of the norm of the d of t for all t greater than or equal to 0. So by defining these two scalars mu and delta, we can rewrite this equation like this. Let's say, so the norm of the signal yf is less than equal to the integral. This part would come as it is. Now if I take the supremum of this one is mu, so this signal, the norm of the signal y of f would also be less than mu and delta. So this part comes here delta, and I have taken the mu common out of this complete equation. Right? So now we define the gain G by this part, which is the supremum of over for all t greater than or equal to 0, and this part. So what we need to prove that if G is finite or not. To basically to prove this implication, 2 implies 1, we only need to show that this G which we have defined by this is finite. Okay. So note that the norm of this complete entity is less than equal to the summation of the absolute value of Gij t comma tau, and this is basically comes from the triangular inequality. This triangular inequality says that the norm of the summation of two matrices is basically less than or equal to the summation of their individual norms. Right? So this is a fact. Now using this fact, we can rewrite this inequality by taking the integral both sides, because it won't change because both the quantities are positive. So I have added the integral both sides, so from 0 to t and 0 to t. Again now taking the supremum both sides, this part you would see once I write the supremum over here, this part is basically what we have defined initially by the summation of the delta. Okay, so from here to here I have done two things. I have added the delta both sides first of all, and then took the supremum. So if I see the first part, basically the left hand side, it is nothing but what we had defined initially, the gain factor G. Now this G is less than this part, which we know is already a finite. So this proves this implication 2 implies 1, because we only need to prove that there exists a gain G which is finite. And by using the properties of the norms, we have actually concluded with the fact that this G is basically finite. Okay. So this proves the first implication, that is 2 implies 1. Now to prove 1 implies 2, let's recall that the force response is given by this one, and this was the definition of the BIBO stability, right? So what we need to prove that the system is, if the system is uniformly BIBO stable, then it implies that every entry of d of t is uniformly bounded, and this condition is also satisfies for every entry gij t comma tau. Okay. Now we'll do the proof of this implication by contradiction, meaning to say what we want to prove that 1 implies 2. We can also prove that if the statement 2 is incorrect or if the statement 2 is false, then it implies that the statement 1 is also false. Okay, so both these implication, either I say 1 implies 2 or negation of 2 implies negation of 1. So both of them are equivalent. So we are going to prove this by contradiction. So let's see. So here we have two parts to prove. First, that every entry of d of t is uniformly bounded. Secondly, that this condition is satisfied. Okay, so first we will see the proof of this, that the every entry of d of t or some entry of d of t is not uniformly bounded. Then it implies the system is not uniformly BIBO stable. The second part of the proof says that if this condition is not satisfied, then the system is not uniformly BIBO stable. Okay. So let's see. Suppose first that 2 is false because the entry dij of this matrix D is unbounded. Okay. So we show next that in this case, taking the supremum of the signal yf for all time t is less than equal to g multiplied by the supremum over all time t of the norm of the signal u of t is also violated, no matter what we choose for the finite gain g, meaning to say that there does not exist any gain g. So to do this, we pick an arbitrary time t and consider the following step input, where this signal u in subscript t of tau defines that whenever tau is lying between 0 and t, the signal is 0, and when the tau is greater than or equal to t, it is ej, and ej is the jth vector in the canonical basis of the k dimensional vector. Okay. So for this input, the second term of the force response at time t is exactly given by y of t is equal to d of t into e of j. Alright, because we know before time t, the input is 0. Now at time t, only this part would remain. This part would go to 0 at time t only. So this is what it is said, that the force response at time t is exactly given by this equation. So what we have found, an input which is bounded, that the supremum of this input what we had defined is basically is equal to 1, and if I take the supremum for all time t of the signal y of t is always greater than equal to y of t, capital T. Because we know that y of capital T would be unbounded, right, which is equal to d of t, and we know some of the entry dij is unbounded, meaning to say that this would be greater than or equal to the absolute value of the dij. So where the last inequality basically results from the fact that the norm of the vector this must be larger than the absolute value of its ith entry, which is precisely dij. This you can visualize by this. Let's say if we have a vector which is given by 1 and 2. Okay, now if I compute the norm of this vector, it would be given by 1 square plus 2 square. Let's take the 2 norm. Okay, the 2 norm of this vector is given by under root 5. Now the norm of this vector is basically greater than the absolute value of all these entries. So root 5 is greater than 1 and root 5 is greater than 2. Basically this part comes from that fact, that the norm of the vector would always be, or it must be, greater than the absolute value of its ith entry. Okay. So since dij is unbounded, we conclude that we can make this part arbitrarily large by using the input for which we know that this input is bounded. Meaning to say that there does not exist a finite gain G. This means that D matrix must be uniformly bounded for a system to be BIBO stable. Because if any entry of the matrix time varying matrix D is unbounded, then there does not exist any finite gain G. Okay. Now the second part of the proof says, suppose the second condition in the second statement is false, right? And why it is false? Because this integral is unbounded for some I and j. Okay. Again, similar to the previous proof, we want to show that there does not exist any g for which this equation or this inequality is satisfied. So again, we pick an arbitrary time t, or we design a signal u, the control signal u, which is bounded. This you can see that we define the signal in the sense that whenever this ijth entry of the g t comma tau is greater than or equal to 0, the input is plus ej, and if it is less than 0, the input is minus ej, and ej is the canonical basis of the n dimensional vector, k dimensional vector, sorry. Okay, so again, if we compute the response at time t, it is given by this one, and its ith entry would be given by this part. So because we know that the ith entry of this part is given by this, and the ith entry of d of t is basically dij. Okay, only at time t. So now what we have found, that although the input is bounded because of the characteristic we have defined earlier, and if I take the supremum of the norm of the signal y of yf is always greater than or equal to the norm of the signal at time t, and at time t, which is basically given by this part, is greater than or equal to the absolute value of its ith entry, which is given by this part, right? Again, using the similar triangular inequalities. So this means that this condition must be true to ensure that there exists a gain G for which the system is BIBO stable. So this completes the overall proof that these two statements are equivalent, that the system is BIBO stable. And the second states that every entry of d of t is uniformly bounded in this condition, or the ijth element of this matrix is satisfied. So let's see for the time invariant case. So for the time invariant system, we have ABCD matrices which do not depend on time, and we also know the state transition matrix for the LTI, which is given by this exponential matrix, where if we are using t comma tau, then it turns into e to the power a into t minus tau. The C and B matrices would remain the same. Okay. So therefore, rewriting from the previous definition is, we can rewrite it as that the supremum of the integral of this integrand should be bounded. Basically, it is the impulse response, that the impulse response should be bounded, with the understanding that now this part denotes the ijth entry of this matrix. Okay. So let's do a change of variable. We replace this t minus tau part by rho. We conclude that if I put t minus tau is equal to rho, then we can replace minus, if I take the derivative of this equation, it would give me d rho. So here d tau would be replaced by d rho. So if I make changes over here, just ignore the supremum for a time being. So we would have the initial limit at tau is equal to 0, we would have the initial limit t, and when the final value of tau is t, rho would be equal to 0. Okay, and we have the, which is a function of rho, and d rho with a negative sign. Okay. Now we can remove this negative sign by changing the order of this integration, which is equivalent to saying that 0 to t, the function inside the absolute value, and d rho, and this is overwritten over here. Okay. Now extend, if we are taking the supremum for all time t, we can extend this time t up to infinity, which eventually give us this condition. So this must be bounded. So this gives us the next result, that the system is uniformly BIBO stable, and for every entry g bar ij of this matrix, we have the absolute value of the impulse response integrated over 0 to infinity is also finite. This also says that the impulse response is absolutely integrable. Right? We can also see the frequency domain conditions for BIBO stability, because we know for LTI system we can use this Laplace transform tool. Likewise, we had seen in the first week. So to determine whether a time invariant system CLTI is BIBO stable, we need to compute the entries Gij of this. To do this, we compute its Laplace transform, and the Laplace transform of this entry is given by C into the inverse of Si minus A into B. Now to compute the ijth entry of this function, it could be written as the ratio of two polynomials, where this is the numerator polynomial and the denominator polynomial, and all these lambdas defines the eigenvalues or the roots of these equations with the multiplicity m. Okay. So if we have m1 is equal to 2, it means that there are two roots located at lambda 1. So we can do the partial fraction of this equation, where we obtain these coefficients a11, a12, which we can compute given the transfer function, and in the denominator we would have all the powers of this first order polynomial. So we have s minus lambda 1 square up to the power m1, which denotes this multiplicity, plus similarly for other elements, and again for the kth one. So now if I take the Laplace inverse to compute the time domain signal, I would have a11 e to the power lambda 1t, plus, because we have this square, by using the property of the Laplace transform, I would have a12 multiplied by t, so this element is added new, plus for the m1th multiplicity we would have a1 m1 t raised to the power m1 minus 1 and e to the power lambda 1t. Now similarly goes for the lambda kth eigenvalue with multiplicity mk. Okay. So we therefore conclude the following. Now if for all Gij of S, all the poles lambda L have strictly negative real parts, then Gij of t converges to 0 exponentially fast, and the system CLTI is BIBO stable. Because first of all, we have already seen that the definition of exponential stability and the asymptotic stability for the LTI system basically remains the same. And since if we look at this part, that the impulse response is basically expressed in terms of the exponentials. Now all these lambdas define the eigenvalues. Now if these lambdas are on the left hand side, all these exponentials would die out to 0 exponentially. So if at least one of the Gij of S has a pole lambda L with 0 or positive real part, then the absolute value of the Gij does not converge to 0 and the system is not BIBO stable. So if we add the d term also, which is a constant term, basically it won't change the location of the poles. So this is the key result in the frequency domain, that the system is uniformly BIBO stable if and only if every pole of every entry of the transfer function of the system has a strictly negative real part. If the eigenvalue or if the pole of every entry of the transfer or any entry of the transfer function is on the 0 or positive, then it cannot be said BIBO stable system. So now there is some relationship between BIBO stability and the Lyapunov stability. So let's explore this for the LTI system. So we know that the LTI system given by these two set of equations is uniformly BIBO stable if and only if every entry G bar ij of this satisfies this condition, meaning to say that it is absolutely integrable. However, if the system is exponentially stable, then every entry of e to the power at converges to 0 exponentially fast, and therefore it must hold, right? So when the system CLTI is exponentially stable, then it must also be BIBO stable. Now this exponential stability is basically in the sense of Lyapunov, meaning to say that if the system is stable or exponentially stable in the sense of Lyapunov, then it must also be a BIBO stable. Given a bounded input, the system would yield a bounded output. But the converse of this statement is not true in general. That is to say that if the system is BIBO stable, then we cannot guarantee that the system is exponentially stable. Let's consider one example to illustrate this situation. Say for example, we have this system given by this ABCD matrices, where A matrix is 1 0 0 minus 2, B vector is given by 0 1, and C is 1 1. So basically it is a single input single output system of a second order, right? So if we compute the state transition matrix of this system, we obtain this, and we know that one of the element is e to the power t, and it is not exponentially stable or unbounded, and therefore Lyapunov unstable. But if we compute this part, we obtain e to the power minus 2 t, meaning to say that this system is BIBO stable. So this is what we want to say, that if the system is BIBO stable, it does not mean or it does not implies in general that the system would also be Lyapunov stable. Right? So these are two footnotes written over here that we shall see in later lectures, that this discrepancy between Lyapunov and BIBO stability is always associated with the lack of controllability or observability. So these two concepts we will see in the later lectures. By the way, that this system, if by the tests or the controllability tests we would going to introduce in the next week, you would notice that this system is not controllable. Right? For the discrete time case, so given A, B, C, D is time varying matrix where T belongs to the set of integers, we have seen earlier that the force response of the system is given by this equation. So the definition of the BIBO stability, in fact for the discrete time system, also remains the same. That if we say that the system is BIBO stable whenever there exists some finite constant G which satisfies this inequality. The time domain BIBO condition for the discrete time LTI system, it is BIBO stable if and only if every entry of D is uniformly bounded and the impulse response is absolutely summable. We can also see the conditions for the LTI system. So we say that the system linear time invariant system is uniformly BIBO stable if and only if for every entry G bar IFJ of CA rho B we have this condition. Okay, and the third statement is basically in the frequency domain, which says that every pole of every entry of the transfer function of the system DLTI has magnitude strictly smaller than 1. Basically it should be inside the unit circle. So there are some interesting facts which we can see now. So consider a function which is defined by this relationship. Okay, this is a continuous time function where n is a integer starting from 2, 3 and up to so onwards. So if we plot this function, this is the plot of this function we have obtained. Now you would notice that the area under every triangle is given by 1 by n square. So we can see also that for the n is equal for some nth value, it is given by half the height n and also the base, which is 2 by n square, which basically comes to 1 by n square. So the area of all this triangle is 1 by n square. So if we compute the integration, we see that the absolute integration of the function is equal to or equals that this summation is a finite summation, because as n increases from 2 to infinity, this summation would be a finite summation. This would approach to 0. So this function we know that is absolutely integrable, but is not bounded and does not approach to 0 as t tends to infinity. So if we would like to see in the discrete time domain, so in the discrete time domain, if g of t or if the signal is absolutely summable, then it must be bounded and approach 0 as t tends to infinity, which is a counter statement to this one, that here the signal is absolutely integrable but it is not bounded. But in the discrete time domain, if the signal is absolutely summable, then it must be bounded and approaches 0 as t tends to infinity. However, the converse is not true, meaning to say that if the signal is bounded and approaches 0 as t tends to infinity, then it may not implies that the signal is absolutely summable. We can see one quick example. Consider the signal g of t is given by 1 over t, where t is belongs to a set of positive integers. Okay, so we compute this summation, taking the sum of the absolute value of g of t starting from t is equal to 1 up to infinity. So we see this summation is given, we can write 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. Okay, now if I start clubbing the entries of this summation, let's say 1 plus 1 by 2 would remain as it is, plus if I combine these two parts, so this part would be greater than 1 by 2. You could see that it would give me 7 by 12. So this part is greater than 1 by 2. Now if I club the next couple of elements, this part is again greater than 1 by 2. Similarly, if I keep combining the elements up to t tends to infinity, I would find that this summation is basically greater than 1 plus every entry is greater than 1 by 2. And we know that this would approach to infinity. So we see here that though the signal is bounded and approaches 0 as t tends to infinity, because the signal it would die towards 0, but here for this particular example that it is not absolutely summable, because the summation is basically infinity. So there are a couple of additional results. So one of the results says that this LTI system or this homogeneous LTI system is marginally stable if and only if all the eigenvalues of the matrix A have 0 or negative real parts, and those with 0 real parts are simple roots of the minimal polynomial of A. So here we are introducing another polynomial which we call the minimal polynomial. Basically this condition is equivalent to one of the conditions we had seen earlier also, but that condition we had seen in terms of the Jordan blocks, which we have introduced on the slide 20, that the system is marginally stable if and only if all the eigenvalues have negative or 0 real parts. So this part would remain same up to here. Now if there are some eigenvalues which lies on 0 or the 0 axis, then they should be simple roots of the minimal polynomial. Now in terms of the Jordan blocks, we had that the Jordan blocks corresponding to eigenvalues with zero real parts are 1 cross 1. So either of these conditions we could use. Either you compute the Jordan blocks or you compute the minimal polynomial, or let's say the eigenvalues of the minimal polynomial. Let's see first how do we define the minimal polynomial. So let A be an n cross n matrix. We associate two polynomials to the matrix A. So first is the characteristic polynomial, which we had already seen, which is given by this function f of s as the determinant of si minus a, where fs is a monic polynomial of degree n. Okay. Now another polynomial we say is the minimal polynomial of a, which we will denote here by psi of s, and is defined by a function having the following properties: that psi of s is monic, that its leading coefficient is equal to 1, psi of a is equal to 0, which it also satisfies. So if I put f of a, it is also equal to 0. So the minimal polynomial should also satisfy this property. In addition to these two properties, it should also satisfy the psi s is the monic polynomial of the smallest possible degree, such that psi of a is equal to 0. Okay. So we will consider some couple of examples by which you would be able to get a clear picture how to compute this minimal polynomial. So there are a couple of other properties, that if g of s is another polynomial, then g of a is equal to 0 if and only if psi s divides that polynomial g of s. And the second one, fs is also a multiple of psi of s. So first we'll consider an example for computing the minimal polynomial. Let's say we have this matrix, A matrix, given as with this specific structure. So if you compute the characteristic polynomial, which is given by the determinant of lambda I minus a, it is given by lambda square lambda plus 1, excuse me. So lambda square lambda plus 1. Now I want to find a polynomial psi of s which is of lesser degree than this. It has a degree of 3 and it also satisfies psi of a is equal to 0. Okay. So a polynomial of less than degree 3 could be a, so there are a couple of options. Let's say psi of a, let's say psi of lambda could be lambda, which is of degree 1, or lambda plus 1, which is also of degree 1. Now there could be a polynomial of degree 2, which could be lambda square or lambda plus 1, and also it could be equal to the characteristic polynomial lambda square lambda plus 1, which is of degree 3. Now if we try to see with all these polynomials whether psi of a is equal to 0 satisfies, then it would be the minimal polynomial. So if we replace lambda by a, we know that A matrix is not a 0 matrix. So this cannot be a minimal polynomial. Similarly, lambda plus 1, if I put A and plus 1, in fact, it cannot be considered as the minimal polynomial, because we are considering only the minimal polynomial where we have lambda is equal to 0. So lambda should definitely be a part of it. Either it would be lambda, lambda square, lambda plus 1, or lambda square, lambda plus 1. So this is in fact, excuse me, that it is not an option for the minimal polynomial, right? So if we take this lambda square, again if I take the square of this matrix, it is again, if I replace lambda by a, it won't be equal to 0. So it is also not a minimal polynomial. Now if I see this part, lambda into lambda plus 1. So if I replace here by a, you would notice that lambda, by putting lambda is equal to a, it becomes equal to 0. So the minimal polynomial of this system is given by lambda lambda plus 1. Now if I compute the eigenvalues or the roots of this polynomial, it contains a simple root only at lambda is equal to 0. Okay, so this says that the matrix has eigenvalues. So there are two eigenvalues at 0 and the third eigenvalue at minus 1. But if I compute the roots of the minimal polynomial, it has a simple root at 0. So this system is a marginally stable system. Now consider another example where here instead of 0 I replace it by 1, otherwise the matrix remains the same. The characteristic polynomial, so sorry, here it should be x. So if I compute the characteristic polynomial for this matrix, it is again equal to this one. But the minimal polynomial of this system is also equal to this one, because there does not exist any other polynomial of lesser degree than 3. And again, if I compute the roots of this characteristic polynomial, we already know that there are two roots available at 0, which are not the simple roots. So this system is an unstable system, and this system is a marginally stable system. Okay. So a time-invariant system is asymptotically stable if all eigenvalues of A have negative real parts. So this is what we have already seen. So now is this also true for the time-varying case? Let's try to answer this question by considering a simple example. Let's say we have this state space system where again sorry I forgot this x. So where A of t is given by this time varying matrix. Now computing the characteristic polynomial of this matrix A of t, it can be written as lambda I minus A of t. So finally this becomes the characteristic polynomial, and it is straightforward to see that the eigenvalues of this characteristic polynomial are at minus 1 and minus 1. So if I apply the eigenvalue test on the LTV system, it says that the system is a stable system because the eigenvalues are strictly at the left hand side. Now we can also compute, or we can also verify it by computing its state transition matrix. So the state transition matrix of this system is given by this, where we could readily see that one of the component is having e to the power t, which means that this system is an unstable system, which also implies that we cannot apply the eigenvalue test onto the linear time varying system. Okay.